Hi everyone, this is lesson 5.2, and I have two topics to talk about in this lesson, general annuities. So in lesson 5.1 we talked about simple annuities and how to develop amortization schedules for them and how to break down the payments into principal and interest. Okay, so we're going to talk about doing the same thing for general annuities. That's going to be the first little piece. We're just going to do two examples doing that. Then we're going to spend the rest of the lesson talking about the final payment. Okay, and specifically, I want to look at where the final payment isn't the same. Okay, so an example of that would be if you have a loan for a certain amount of money, let's say $5,000, and you can only afford each month to put $200 down on that loan. So if we don't use our annuity formulas to calculate the payment and come up with a number, picking a number like $200 would often result in your last payment not being equal. Okay, so it would be a partial payment or less than that $200. Okay, so we're going to look at a method. There's several steps you have to do in that method. So we're going to look at how to figure out what that final payment would be. Okay, so starting off, again, looking at a general annuity, you'll remember from everywhere else in this course that there's two major changes. First of all, the interest number of interest compounding periods and number of payment periods per year are not the same in a general annuity. So you have to calculate a ratio C. And then with that, you calculate an equivalent rate of interest using that ratio C and using the periodic interest I. Okay, so that develops this interest rate, which we call the letter P. So when we try and find the payment, it's the exact same formula as a simple annuity, except everywhere I was, we've replaced it with this equivalent rate of interest, P. So those were the only changes for these formulas. So otherwise, everything that you're going to see in these two examples we do is the same as we did last lesson, just replacing it with that equivalent rate of interest P and adding in these additional two calculations. So our first example, a debt of $30,000 has interest at 9.75% per annum compounded quarterly. Payments are at the end of each year for the next 7 years. So we have three parts here. Part A is what is the size of your yearly payment. Okay. Part B, what is the interest amount on your first payment? And part C, what is the outstanding principal balance after the first payment? Okay, so a couple items to note here. So interest is compounded quarterly, payments are yearly, and payments are at the end of each year. So that makes it an ordinary general annuity. And remember, for your Unit 4 test, I'd like you to write whether or not what type of annuity it is at the start of your answer. Okay, so getting into that habit is still important in Unit 5. So part A is asking for our yearly payment. So we start with our formula. Payment is equal to our present value, and I use the subscript G, remember, for a general annuity, multiplied by the equivalent rate of interest, P, divided by 1 minus 1 divided by 1 plus the equivalent rate of interest, P, to the exponent n. N in this case being the total number of payment periods. Okay, so starting my sidebar again on the right, our present value for this general annuity, in this case it's a debt of $30,000. Our nominal rate of interest, J, is 9.75%, which is 0.0975. M, our number of interest compounding periods, it's compounded quarterly, so M is 4. So our periodic rate of interest, I, is J divided by M, which is equal to 0.0975 divided by 4. And that comes out to an I of 0.024375. You'll notice I kept a lot of decimal places there, and that's because this is an exact number. Okay. So next, our value for C the number of interest payment periods divided by the number of payment periods per year. In this case, interest is compounded quarterly and payments are yearly, so 4 divided by 1 gives you a value for C of 4. So this gives you our equivalent rate of interest P is 1 plus I to the exponent C minus 1, or in this case, it's 1 plus 0.024375 to the exponent 4 minus 1. So our value for P comes out to 0.10112. Okay, and I'm running out of space, so I'm going to put this up top. Our last calculation is N. So in this case, we're making payments once per year for 7 years. So 7 years multiplied by 1 payment per year gives you a value for N of 7. So if you substitute these values in, our payment is equal to 30,000 times our equivalent rate of interest, 0.10112, divided by 1 minus 1 divided by 1 plus our equivalent rate of interest, 0.10112, to the exponent 7. Okay? And if you calculate that out, you'll get a payment of $6,189.80. Okay? So part B asks for what is the interest on your first payment. So remember, it's the same way we did it in the previous lesson. Our outstanding principal when you're at your first payment is still $30,000. It's the start of your debt, right? Because you haven't paid any off. So it's simply $30,000. But in this case, it's multiplied by the equivalent rate of interest, not the periodic rate of interest. In this case, 0.10112. And if you calculate that out, all right, you get an interest of $3,033.60. So for part C, now, what is the outstanding principal balance after the first payment? Well, first, we have to figure out how much of our payment is actually paying off the principal. So what's that breakdown? So that's equal to our payment, 6,000, oh, put the decimal or the comma in the wrong place, $6,189.80 minus $3,033.60. And that comes out to $3,156.20. So that is the amount of principal that you're paying off on your first debt payment. Okay? So that means that you've paid off a total, or your new, outstanding principal balance is equal to your debt, which is in this case $30,000 because you haven't paid any yet, minus the amount of principal you're paying off on this payment. Okay, so it's 30,000 minus $3,156.20. That gives you $26,843.80. Okay, and remember, you saw this when we did the Excel lesson, that as you make more payments, the amount you pay in interest decreases because the amount you have for your principal is less, and the amount you pay off on your principal increases. Okay, you'll especially see that when you see the long amortization schedules, like we did in lesson 5.1, part 2. Okay. Okay, so our second example for general annuities. A loan of $12,000 is to be paid back with payments at the end of each quarter for 4 years. Interest is 5% per annum compounded semi-annually. What is the size of your quarterly payment is part A. Part B is what is the interest amount on your first payment. Part C, what is the outstanding principal balance after the first payment. And part D, what is the outstanding principal balance after the second payment. Okay, so similar to some of the last questions we did in lesson 5.1. First things I'd like you to notice, payments are at the end of each quarter, and they're made quarterly while interest is compounded semi-annually. So those are not the same. So that makes it an ordinary general annuity. Okay, so part A, We're looking for our payment. So remember, payment is equal to the present value, and I use the subscript G again for a general annuity, times our equivalent rate of interest divided by 1 minus 1 divided by 1 plus the equivalent rate of interest P to the exponent n. Remember, n in this case is the total number of payment periods. So a couple items we know. The present value given in the question is $12,000. Our nominal rate of interest J is 5%, which is equal to 0.05. M, in this case, okay, interest is compounded semi-annually, so M is 2. So I is equal to J divided by M, or 0.05 divided by 2, which gives you 0.025. Next, because it's a general annuity, the calculation of the ratio C, it's the number of interest payments divided by the number of payment periods. Sorry, interest compounding periods divided by payment periods. In this case, interest is semi-annual, but payments are quarterly. So 2 divided by 4 gives us a ratio of 0.5. So that gives us an equivalent rate of interest P of 1 plus the periodic rate of interest C minus 1. So in this case, it's 1 plus 0.025 to the exponent 0.5 minus 1. Sorry, I thought I had more space than that. And that gives you an equivalent rate of interest of 0.01242. Okay? Our last item here, N. Okay, in this case, payments are for 4 years, and they're made quarterly. So it's 4 times 4 gives you a value of 16. So if you substitute all these values in, our payment is equal to our present value, 12,000, multiplied by our equivalent rate of interest, 0.01242, divided by 1 minus 1 divided by 1 plus the equivalent rate of interest, 0.01242, to the exponent 16. Okay? If you calculate that out, you get a payment of $831.62. So just like in the last question, okay, now we're going to break this down into interest and principal. Okay? So part B, what is the interest amount on your first payment? Again, we haven't made a payment yet on the loan. So the amount we have outstanding is $12,000. And we multiply that by the equivalent rate of interest, in this case P, which is 0.01242. And if you multiply that out, you get $149.04. Okay? So compared to the last question, what you'll notice is interest is relatively small compared to our payment, right? Meaning we're going to pay more off in principal, okay? So part C is asking, what is the outstanding principal balance after the first payment? So our first step was, again, figuring out how much we're paying off in principal, and that's equal to the payment, $831.62, minus the interest, $149.04. So that is equal to $682.58. So you can see, if you look at that ratio, you're only paying $150 in interest to $680 in principal. Okay? In the previous question, it was almost more like a 50-50 split. Okay? So that depends on a lot of factors, how long your loan is for, and how high or low your interest rate is also plays a role. But again, as I mentioned, as you make more payments and reduce your principal, your interest will go down and your principal payment will go up each payment. Okay, so you see that when we build amortization schedules. So now that we have the principal, we simply subtract that from our loan. So our outstanding principal balance is $12,000 minus the $682.58 principal payment that we made as part of our first payment. And that gives us $11,317.04. Okay, so part D is asking about the outstanding principal balance after the second payment. So again, we follow the same steps we did in parts B and C. First, we calculate the interest, which again is how much we have remaining on our loan, $11,317.42, multiplied by the equivalent rate of interest, 0.01242. So in this case, that number works out to $140.56. Again, you can see how the interest decreased because you have less on your loan to repay. Okay? So now we figure out how much we're paying off on the principal. So we take our payment, $831.62, and we subtract the interest, $140.56, and we get $691.06. So again, I keep bringing this up, but it's important. You can see that while our interest, the amount we paid on interest went down, the amount we're paying off of our actual loan, so paying off on the principal, increases. And that will happen with every single payment that you make. Okay? So our last step is to just find the outstanding principal balance. So we started with $11,317.42 because we already made one payment, minus $691.06, the amount we're paying off in this payment for principal. And if we do that, we get $10,626.36. Okay, so they'll keep decreasing time and time and time again. All right. So now we're going to look at something a little bit different. You'll notice that when we did simple annuities and general annuities for amortization, we always calculated the number or the payment value knowing a set number of payment periods. So in this area, we're going to kind of do the opposite. So we're going to have a set payment, and we need to calculate the number of payment periods to pay off that loan. Okay? And what happens is when you do it that way, it's very, very rare that you're going to end up with an even number of payment periods, or in other words, an even value of n. Okay? A lot of times you'll end up with a value that's a fraction. In this case, an example I used was 6.48. Okay? So in previous examples, I always rounded up and said you need to make 7 payments. Okay, but what happens is your last payment is actually a reduced amount of money. Okay, because you only have a fractional amount of money left on your loan to pay. Okay, so this is a method of determining what your final payment is going to be. So it's a little bit more complicated in terms of steps. So I'm going to show you 6 different steps that you have to follow to solve this. But once you kind of get used to it, we're going to go through 3 separate examples. I think practice will make this become a little bit easier for you. So in every one of our steps, every one of our questions, the first step to look at is going to be finding the value of n. So I've showed you both these formulas because you're going to have to determine whether it's a general annuity or a simple annuity. Okay, so for both these, payments will, in questions I gave you, be at the end of the period, and that's because we didn't go over how to do the hand calculations for calculating n for annuities due, and that was just because the math got a little more intense. So instead, I had you do that in Microsoft Excel. Okay, so it's always going to start with calculating n. All right, so keep these formulas in mind. Again, they're the same formula. The only difference is for general annuities, you use the equivalent rate of interest P instead of the periodic rate of interest I. And remember, the equivalent rate of interest P is 1 plus the periodic interest rate C, or to the exponent C minus 1. Okay? So these are the steps. Again, I'm going to go over each step right now. And I have this here more as a placeholder for you to have this available while you're answering the question until you get used to the steps. So I'm going to go over them now, and it's going to seem like there are a lot of steps, and you know, there are, I mean, having six steps, but I'm going to walk through in the next 3 questions how to just go step by step by step. So having this printed out or having this with you when you do questions is very valuable. So the first step, like I said when I talked in the previous slide, is you have to find the number of payment periods n. So that is whether or not it's a general annuity or a simple annuity, you just use one of those 2 formulas. The second step is to determine how many full payments will be completed before the final payment. So if you remember, if you have a fraction of a payment, let's say it's the 6.48, what that means is that you're going to make 6 full payments and then a fraction of a payment, okay, which would be this 0.48. All right. So then what you do, all right, is looking at the timeline. Okay, so let's look at this example. If we had to make 6.48 payments, here we are today, and here we are 6 payments from now, and this is the end of the loan, which would be 6.48 payments. What we're going to do is we're going to find the future value of our original loan using compound interest at this point. Okay, so we're right at our final payment. Okay, so we've made 6 full payments and we've got a piece left. Then in our next step, we're going to do the same thing and find the future value of all your payments up to right before the final payment. In other words, using the future value formula for an annuity. Again, I'll do that one in blue. That's to translate all of those up to this period in time, which is right before your final payment. Okay, so you're going to have 2 values. The value of your loan translated to that period in time, and the value of your annuity, the future value, to that period in time. The 5th step is to simply just subtract the 2. So you subtract the number you get in step 3 from the number you get in step 4. So this is simply the step 3 number minus the step 4 number. Okay, so what that does is it gives you an amount of money that you have left in your loan to pay, right? Because in step 3, you did the future value of that whole debt. And in step 4, you did the future value of all the payments you've made so far. And remember, all the payments you've made isn't going to pay off your whole debt because you still have a piece of a payment left, right? So when you subtract them, you'll come up with a number, and that's how much you have outstanding right here, okay? Right before your final payment is made. So because I'm giving them to you at the end of the period, your last step is you have to then add interest to it, right? Because it's going to accumulate interest till you pay your last payment off at the end of the period, right? Right at the end of that period. So what you do is you take the number from step 5, I'll call this the step 5 number, and you multiply it by either the periodic rate of interest, I, or the equivalent rate of interest, P. And that just depends on if it's a general annuity or a simple annuity. Okay? And all that's doing is accounting for the little bit of interest you're going to have up until you make your final payment at the end of the period. Okay? So again, these are a lot of steps, but I'm going to walk you through each of these steps in 3 examples. Okay, so let's look at our first example. Bronco Repairs borrowed $15,000 from National Credit Union at 10% interest per annum compounded quarterly. The loan agreement requires payments of $2,500 at the end of every 3 months. What is the size of the final payment? So it's only one part, right? What is the size of the final payment? But again, you gotta follow these 6 steps that I showed you in the previous slide to solve this. So I'm going to go over each of these steps and I'm going to label them. Okay, so you can go back and look at these and see how it kind of is created. Okay, so first thing to note, okay, payments are at the end of every 3 months or quarterly, and interest is also quarterly. So this makes this an ordinary simple annuity. Okay. So I'm going to start with step 1. Okay, and that's finding n. So in this case, it's a simple annuity. So you use the formula for n, which has ln 1 minus the present value of a simple annuity, that's how you use subscript n, times the periodic interest rate divided by repayment. And that's divided by the negative ln of 1 plus the periodic interest rate. So again, my sidebar, what do I know in this question? Our present value, in this case, is 15,000. Okay, that's what our loan is worth today. Call it at time 0. Our nominal interest rate, J, is 10%, which is equal to 0.10. Our number of interest compounding periods is quarterly, so M is 4. So this gives a periodic interest rate, I, which is J divided by M, of 0.10 divided by 4, or 0.025. And lastly, their payments are $2,500. Okay. You'll see this a lot when you have very even payment numbers as opposed to our previous questions, which are always payments with decimals, right? And that's because you have an equal number of payments. So if we calculate n, all right, substitute all these values in, we get the ln of 1 minus 15,000 times our periodic interest rate, 0.025, divided by our payments, 2,500, and that's divided by the negative ln of 1 plus the periodic interest rate, 0.025. Okay, so the same thing we've done in the past solving for n. So if I do this in steps, n, this comes out to the ln, in the numerator comes out to 0.85, and then denominator is the negative ln of 1.025. And if you calculate that out, you get 6.58. So again, you see we have a fractional payment. So our step 2 is to figure out how many payments, right? How many full payments are we going to make before we have a fractional one? So we have 6.58. So that means we're going to have 6 full payments. Okay? So what that means is we use that value of 6. That becomes our value of n, right? Because that's the number of payment periods we're translating into the future. Okay? So if I look at that, what that means is, so we are here today, time 0, and we've got a value of $15,000 on our loan, and we're making payments of $2,500. What I'm going to do is find the future value after we've made 6 payments, okay? Because the end of the loan, if you're looking at payments, is 6.58, or a fractional amount. Okay, so this is the time period we're trying to get to. Okay, and then you'll see that in my next 2 steps. So our third step is to use compound interest and to take this 15,000, our present value of our loan, and find the future value of it all the way here at the time of our last payment. Okay, so if I do that, again, I'll do it in the same color that I just circled those in. Then our future value is equal to our present value times 1 plus the periodic interest rate to the exponent n. In this case, we're going 6 payment periods, right? We just figured that out. And we know all the other terms. Our present value is $15,000. And our periodic rate of interest that we calculated is 0.025. So we simply substitute those values in. 15,000 times 1 plus 0.025, our periodic interest rate, to the exponent 6. And we get a future value of $17,395.40. Okay, so that's the value of your loan after 6 payment periods, $17,395.40. Okay, so now, okay, I'm going to go to another slide to continue our steps. So now we move to step number 4. Okay, so I'm going to draw that same graph we had. Today's times 0. We're trying to get to times 6. And our final payment is a fractional payment. Okay, so we started with $15,000 here, and our future value was $17,395.40. So now we have to find the future value of the annuity, making those payments of $2,500 to figure out what it's worth. Again, looking at this time period of 6 payment periods from now. So to do that, we use the future value for an ordinary simple annuity. So the future value is equal to the payments times 1 plus your periodic interest rate to the exponent n minus 1 divided by your periodic interest rate. So we know all of these variables from the question. So our future value is equal to our payments. Remember, $2,500. It's also given up here. Multiplied by 1 plus the periodic interest rate, 0.025. And we're going to the exponent 6. Remember, we're moving 6 payment periods into the future. Minus 1 divided by our periodic interest rate, 0.025. Okay? And if you calculate that out, all right, you get a value of $15,969.34. So step 5, if you remember, is to subtract the value from step 3 minus the value of step 4. So in this case, the value we calculated in step 3, that was what our loan was worth 6 periods from now. That was $17,395.40. See that value here. And we're subtracting off the value we calculated in step 4, which is $15,969.34. And if we do that, we get a value of $1,426.06. So what this means is at this period in time, okay, at payment period 6, we would have an outstanding loan of $1,426.06. Now, since we don't pay it till the end of the period, it's going to have interest associated with it. So our final calculation is just going to add that interest to it. Okay, so step 6 is to take that value, $1,426.06, and multiply it by that periodic rate of interest. How much interest the remainder of your loan will earn in that last period. In this case, it's 1 plus that periodic rate of interest, 0.025. Okay? And if you calculate that out, you get $1,461.71. Again, this term is simply 1 plus I if it's a simple annuity, or 1 plus P if it's a general annuity. Remember, it has to be 1 plus the interest rate because you have to keep this original balance, right? That's what that 1 is there for. So this would be the size of your final payment, $1,461.71. Okay? So you'll notice that it's quite a substantial decrease from the $2,500 you paid at the start. Okay, let's look at our second example using these same steps. On his retirement, Art received a bonus of $8,000 from his employer. He invested his money in an annuity that provides for payments of $1,200 at the end of every 6 months. If interest is 6.25% per annum, compounded semi-annually, determine the size of the final payment. Okay, again, we're going to do this in steps. All right, so first item I'm going to look at before I start my steps. Payments are at the end of every 6 months, and interest is also compounded semi-annually, which is every 6 months, so it's the same. So, just like the last example, this is an ordinary simple annuity. And if you already are not in the practice of it, I do want you to write what type of annuity it is at the start of every one of your answers to an annuity question. Okay? Just helps to get you started on the right path. So, we're going to start with step 1. And step 1 is always finding n. So n, in this case, it's a simple annuity. So it's the ln of 1 minus the present value for a simple annuity times the periodic interest rate divided by the payment divided by the negative ln of 1 plus the periodic interest rate. Okay, that was a bad I. So, what do we know in this question? Again, our present value in this case is $8,000. That's how much he's starting with, okay? The nominal rate of interest, J, is 6.25%, which is equal to 0.0625. Interest is compounded semi-annually, so M is 2. So our periodic rate of interest, I, which is J divided by M, is 0.0625 divided by 2. Or in other words, I is equal to 0.03125. Okay, and again, I use a lot of decimal places in that case because it's an exact number. Our last item we need is our payments. So his payments in this case were $1,200. Okay, substituting these values in, we get the ln of 1 minus our present value, 8,000, times our periodic rate of interest, I, 0.03125, divided by our payments, which is 1,200, divided by the negative ln of 1 plus 0.03125. Okay? If we calculate those out, we get n is equal to the ln of 0.7916. It's actually a repeating decimal. Let's put a bar. Divided by the negative ln of 1.03125. And if we calculate that out, we get 7.59 payments. Okay, again, it always will work out to a fractional number. So step 2, how many full payments are we going to make, right? So we had 7.59 payments, so that means we're going to make 7 full payments. And then a partial payment for the last one. So that means that 7 is your value for n. Okay? Third step now, right? Again, starting with our graph here, we're at today. We're going to move forward 7 periods or 7 payment periods into the future. And we're eventually going to end up at the very end, figuring out our final payment at the end. Okay, so step 3 is to find the future value, remember, of our original principal of $8,000. So our future value is equal to our present value times 1 plus the periodic interest rate to the exponent n. Again, we're starting with $8,000 here. So our future value is equal to 8,000 times 1 plus the periodic interest rate, 0.03125. And that's the exponent 7, because we are going 7 payment periods into the future. And if you calculate that out, you get $9,922.88. So that means at this point in time, that money would be worth $9,922.88. Okay, that's in other words the value, the future value of this principal. Okay, so our fourth step is now to find the future value of that annuity for all the 7 payments that you've made. Remember, we're going to compare those two numbers in step 5. So that means it's the future value, and I use n because this is an ordinary simple annuity, and it's equal to the payment times 1 plus the periodic interest rate to the exponent n minus 1 divided by the periodic interest rate. So what that means is it's equal to the payments, which is $1,200, times 1 plus the periodic interest rate, 0.03125. And this is to the exponent 7. Again, we're moving 7 payment periods into the future. Minus 1 divided by 0.03125, the periodic interest rate. If you calculate that out, you get a future value of $9,229.82. Okay? Remember, going back to our timeline, we're at time 0. We've now translated both those, the annuity and our principal, to this payment period in the future. Remember, we started with $8,000. Our future value was $9,922.88. And our future value of the annuity is $9,229.82. So now in step 5, we simply find the difference between those two. So step 5 is the difference between step 3 minus step 4. In this case, $9,922.88, the total amount of principal we had, minus $9,229.82. And if we do that, we get a value of $693.06. So again, that's the outstanding amount of principal we have, $693.06, right after we've made our 7th payment. So, because payments are at the end of the period, we have to add that periodic rate of interest to it to figure out the total amount we have left, right? Because we always are paying a bit of interest and a bit of principal. So step 6 is that outstanding balance, $693.06, multiplied by 1 plus, in this case, the periodic rate of interest, because it's a simple annuity, or 0.03125. So if we calculate that out, we get a total amount of $714.72. Okay? So again, following these steps, you can follow these steps to get to the answers for each one of these questions. I know it's a long way to do the question, but it's an easy way for you to figure out that final balance if you just continue to follow these steps each time. So our final question is going to take it a step further. Remember, we also talked about deferred annuities. Okay, so this question's got one more extra tweak at the start of the question that you'd have to keep in mind when looking at these. Payments of $500 deferred for 9 years are received at the end of each month from a fund of $10,000 deposited at 10.5% per annum interest compounded monthly. Determine the size of the final payment. Okay, a couple items to note here. First of all, it's deferred. Payments are at the end of each month, so that makes it ordinary. And your interest is compounded monthly, and your payments are also monthly. So this makes this an ordinary simple annuity that's being deferred. Okay, so it's one shift we have to do at the start before we can do our 6 steps. Okay, so I always like to start with a graph. So we're here today. We're going to 9 years in the future first. Okay, that's our first step. Remember, from a deferred annuity is to go to that period in time. Then we can start our steps where we take that the future value that we calculated here, and we start to calculate n, and we start to then do another future value calculation, because we want to get to another point here we don't know where that is, where we've made all of our full payments. And then we have to go our last step to figure out our final payment, okay? So we started, all right, with a fund of $10,000, all right? So what we have to do is we actually have to find the future value of that fund at this period in time, because that's how much money they're going to have in their fund to start paying out these payments of $500, okay? Because it's being deferred for 9 years. So to start with that, okay, we're going to have the future value is equal to the present value times 1 plus the periodic interest rate. And that's the exponent n. This is an exponent. This n is just related to your payment period, translating it from today to 9 years in the future. Okay? So our present value in this case is equal to $10,000. Our nominal rate of interest, J, is 10.5%, which is 0.105. Our number of compounding periods, interest compounding periods, it's compounded monthly. So that gives you M is 12. So our periodic rate of interest, I, is J divided by M, or 0.105 divided by 12, which gives you 0.00875. Lastly, okay, our value for N, in this case, we are going 9 years in the future times 12 interest compounding periods a year gives you 108. So if you substitute these values in, you get 10,000 times 1 plus 0.00875 to the exponent 108. And if you do that, you get a value of $25,622.60. So that's the value of this fund when we start having payments right at 9 years in the future. So $25,622.60. So if it's deferred, remember you have to do that calculation first before you can follow the 6 steps. Okay, so now we have our amount of money that we're starting with here. Okay, so our first step is to solve for N. Okay, in this case, it's an ordinary simple annuity. So N is equal to the ln of 1 minus the present value of a simple annuity, that's why I use the subscript N, times our periodic rate of interest divided by our payment. Okay, that's all divided by the negative ln of 1 plus the periodic rate of interest. So if you substitute, we know all these values, right? So our ln of 1 minus, we know our present value because we just calculated it at the start of the annuity, $25,622.60, multiplied by the periodic rate of interest, 0.00875, divided by our payments, again given in the question, of 500, and that is divided by the negative ln of 1 plus 0.00875. Okay? And if you calculate that out, you get a value of N of 68.29. Okay? So for step 2, that means we have 68.29 payments, or we have part of it that's a fractional payment. That means we're going to make 68 full payments. So our value of N for our calculations in step 3 and 4 is equal to 68. Okay? So if we move to our third step, okay, now we have to translate this amount of money, the $25,622.60, 68 periods into the future. Okay, so in order to do that, we have to use the simple future value formula. So the future value is equal to the present value times 1 plus the periodic interest rate to the exponent n. Again, because we're just taking this principal that we have today and translating it all the way to this period in time, which is actually 68 payment periods into the future. So if we substitute what we know, our present value is $25,622.60. Again, this is present value of our pool of money we have here, multiplied by 1 plus the periodic rate of interest, 0.00875, and that's to the exponent 68. Again, we're moving 68 periods into the future. Okay? And if we calculate that out, we get $46,334.50. Okay, so that's the value of our pool of money, in this case because they're earning payments. Okay, so that's the value of that money right at the last payment. In other words, payment 68. So if we move to our fourth step, I'm going to just draw our timeline again to see what we've solved. So we started at time 0, okay, and we went 9 years into the future. And we started with $10,000, and we translated that forward to $25,622.60. So that was when payments started, okay, so 9 years from now. And then we had to move that further. After we solved for n, we said we'd get 68 full payments out of it. So we went 68 payment periods into the future, and that value of money was then worth $46,334.50. So that's right before our last area, which would be 68.29, when we've paid it all off. Now, we've got to find the future value of the annuity. Okay? So again, it's a simple annuity. So the future value is equal to the payment times 1 plus the periodic rate of interest I to the exponent n minus 1 divided by the periodic rate of interest I. So in this case, our payments are $500, and we know our periodic rate of interest is 0.00875. So that's the exponent 68, because we're going 68 payment periods into the future, minus 1 divided by our periodic rate of interest, 0.00875. Okay? If you calculate that out, you get a future value of $46,191.13. Okay? So, I'll do that in a slightly different color. $46,191.13. So again, that's comparing your annuities value, in other words, how much you've been paid out of the annuity, to the future value of just the balance we started with. Okay? So step 5 is simply step 3's value minus steps 4's. In other words, $46,334.50 minus $46,191.13. And if you calculate that out, you get $143.37. So you can see it's far less than the $500 payment that you would have otherwise received. And again, remember, because payments are at the end of the period, this amount will still accumulate a little bit of interest. So our final step is to actually calculate including interest. So we have $143.37, and we have to add that interest, in this case 1 plus the periodic rate of interest, 0.00875, and we get a value of $144.62. So that would be their final payment at the end of that period after it's accumulated all of that interest. Okay? So this was the most complicated example, having it be deferred first. So we basically just did 2 future value calculations with compound interest. Okay? So that was all I had for this lesson. I do have some examples you can look at in the textbook. I do encourage you to become more familiar with those steps to do this final payment. It's one of the more complicated annuity calculations you can do. From Unit 4, the deferred annuities, again, was also one of the more complicated aspects. Okay? If you do have questions, please send me an email. Thanks.